Hey Bengals, this is Miss Timmons here. Today we're going to be looking at the law of conservation of mass and talking about what the law is, how to do balanced chemical equations, how do balanced chemical equations support the law, and then we'll talk about some examples and how you determine whether a chemical equation is balanced or unbalanced. So, to start out with, we need to review what is a chemical equation. And a chemical equation is just your shorthand way of showing what takes place in a chemical reaction. So in this case, we have sulfur, which is the S, plus iron, Fe, will give you iron sulfide. So you mix it together, you add heat, and it creates iron sulfide. This is just your chemical equation. It illustrates what happens in a chemical reaction. So then we need to talk about what the law of conservation of mass is. The law of conservation of mass states that matter cannot be created or destroyed, only rearranged. It's very similar to the law of conservation of energy. Basically what it means is however many atoms of a substance you start with, you have to also end with that same number of atoms. But it also is true about the mass, and we'll look at a few examples of both. So if you look at this equation down here at the bottom, you have calcium carbonate down here, the CaCO3, will give you a reaction, after a reaction it'll give you calcium oxide and then carbon dioxide. So it breaks down into those two substances. Now, to determine whether or not this equation is balanced, you have to go back to the steps of training wheels and be able to count the number of atoms in a formula. These are fairly simple. So what you have to determine is, do I have the same number of each element on both sides of the equation? So if you look at just the calcium, I have one atom of calcium in the reactants, I have one atom of calcium in the product. So for calcium, we're balanced. If you then look at carbon, carbon has one in the reactants, one in the products. And then oxygen has 3 in the reactants, and then 1, 2, 3 in the product when you add those two together. So that means that each of these elements has the same number of atoms on both sides. Therefore, this equation is in fact balanced. So I want to take a look at a couple of examples of balanced equations. So we talked briefly about how it pertains to the number on both sides, but I also want you to see that it also pertains to the mass. So the mass that you start with on the left has to equal the mass that you end up with on the right. So check out these reactions, or this one reaction. Okay, so in this particular reaction, we started with a substance that had 2 clear liquids, and they put everything into a flask with a stopper on the top, and we started with a mass of 158.2 grams. Then they turned the flask over with the stopper still on it. They turned the flask over so that the two substances could mix. So you started with lead nitrate and potassium iodide, and ended up with potassium nitrate and lead iodide. And when the two mix, they instantly create a yellow solid, which is the lead nitrate or lead iodide. Notice though that the final mass is still 158.2 grams. So the amount they started with and the amount they ended with was the exact same. This follows the law of conservation of mass. The stuff you start with is the stuff that you end with. Okay, so this equation kind of gives you a different representation for how you may see chemical equations, and that is using shapes to represent the different elements. So in this case, we have these substances. We have three triangles. Excuse me. Three triangles, you have a rectangle and a circle all bonded together, and that represents the calcium carbonate. And then on the right hand side, you have the one rectangle, the one triangle, and then one circle and two triangles. Ultimately though, you have the same number and type of shapes on both sides of the equation. Make sure that not only the number but the type of shape are the same. So in this case, the circle represents the carbon, the rectangle represents the calcium, and then the triangle represents the oxygen. And then they're the same number and types of shapes on both sides.
So we need to find a way to determine whether the equation is balanced or unbalanced, and in order to do that, we use a chart known as the ERP chart, or the ERB chart, depending on who you are and how you want to talk about it. So ERP, E stands for the number of elements, and in the E category or column, you would just list all of the elements found in the reaction. The R stands for reactants, and that is where you write the number of that particular element found in the reaction or in the reactants, and then P stands for product. So let's use this particular equation to practice using the ERP chart. So in this case, I start by listing my elements. So the first element I have is Fe, which is iron, and then I also have oxygen. So I list my two elements. So then I go back and I figure out how many elements or atoms of that element I have in the reactant side. The reactant side, remember, is the left. So in the reactant side of this equation, I have one atom of iron, so I'll put a 1. In the reactant side of the equation, I also have, if you multiply these out, oxygen is 3O2. So oxygen has a 2 for a subscript, and then a 3 for a coefficient, which gives me a total of 6 in the reactant. And then I move to the product side. Now the product side is on the right. Okay, so in the product side of the reaction, I have 2Fe2O3. So for iron, 2 times 2 is 4. So I have 4 irons. And then 2 times 3 is 6. So I have 6 oxygens. That means this particular equation, because of this element right here, the iron element, and the fact that there's not enough irons on the left side and the reactant side, this particular equation is unbalanced. Okay? Let's move on to a different one. So we'll follow the same steps using this next equation. So the first thing that I do is write down all of the elements that I have. So the first one I have is potassium, which is K. And then I have hydrogen, and then I have oxygen. So let's go back and count. For potassium, I have 2 on the left, so I have 2 in the reactants. For hydrogen, I have 4, because 2 times 2 is 4. And then for oxygen, I have 2. Okay? Again, if you're struggling with figuring out how many you have, go back to the steps for training wheels. Okay? Keep using those steps until you are really confident in figuring out these numbers. So then we move to the product side. The product, I have 2 potassiums because of the coefficient of 2. And then I have 2 oxygens. And then I have 2 hydrogens in this formula, but then I also have another 2 hydrogens over here. It's listed twice. Make sure you count it twice. So I have a total of 4. Because each of these are equal, that means this one is balanced. Alright, one last one that we're going to try. So again, we're going to list all of our elements. I have sodium, Na. I have hydrogen. I have carbon, and then I have oxygen. So on the reactant side, I have 1 sodium, 1 hydrogen, 1 carbon, 3 oxygens. In the product side, I have 1 carbon right here, and then I have 2 oxygens here, but then I have another one over here for a total of 3. I have 1 sodium and then 1 hydrogen. So again, this one is balanced because all of these elements are equal on both sides. Okay, now, the ERP chart works very similar to your training wheels. When you get to the point where you can easily, without using the chart, figure out whether it's balanced or unbalanced, then stop using the tool. However, until you get to that point, you've got to keep using the tools that you're given and use the ERP chart. Thanks, guys, and y'all have a great day.